Swayam Prabha. Digital India. Educated India.
Namaskar. So, in last session we started our discussion about the three phase circuits, and last we discussed about the star star balance circuit, that means you can also say YY balance circuit. So, in today's session we will discuss about Y delta as well as delta delta circuits. So, let us start our discussion related to first we will discuss balanced Y delta connections. So, you will see there we have a Y delta circuit where the source is connected in a star, or you can say Y, and load is connected in delta form. So, you will see that the A phase of the source is connected to A of load, B is connected to B of load, and then C is connected to C phase of the load. So, in this way you can say that the star source is feeding power to the delta connected load. Now, if you see this particular arrangement, you can simply say that we do not have neutral connection between the source as well as load. Now, if we assume the positive sequence, the phase voltage, or you can also say line to neutral voltage, will be VAN will be VP angle 0. VP is means RMS voltage per phase. So, VP angle 0 degree will be the VAN. VBN will become VP angle minus 120 degree. If you remember, when we discussed about phase sequence, we told that ABC sequence will have the angle difference of 120 degree, and the B phase will lag A by 120 degree, and C will lag B phase by again 120 degree. So, your VBN will become VP angle minus 120 degree, VCN will become VP angle minus 240 degree, or you can also say VP angle plus 120 degree. Now, when we discussed about the star star connection, we discussed about the phase voltage as well as line voltage. So, in this case also the line voltage will be VAB. So, since the source is your star connected, so you will see that the line voltage will be VAB, and we derived that the value of VAB will be root 3 VP angle 30 degree. So, this is what we derived when we discussed about the star star connection, balanced star star connection of the circuit. Similarly, VBC will become root 3 VP angle minus 90 degree, VCA will become root 3 VP angle minus 210 degree. Now, if you see this particular arrangement, the line voltage of the source will be equal to phase voltage of the load, because line voltage, that is VAB, is coming across the phase AB of the delta. So, what we can write, that VAB will be equal to the capital V capital AB, that is the load phase voltage. VBC will be equal to VBC, and VCA of the source will be equal to VCA of the load. So, here if you see this particular arrangement, you will come to know that in case of delta connected load, or if in case of delta connected source, the phase voltage will be equal to line voltage. So, whenever we see the delta connected source or load, we will say that the phase voltage of the delta will be equal to line voltage of the delta, whether it is source or load. So, we can say that line voltage are equal to voltage across the load impedances for this system configuration. That means, line voltage will be equal to phase voltage coming across the load impedance. Now, from the voltage values which we got, we can find out the value of phase current. So, phase current will be IAB. So, that is the current flowing in leg AB. So, this will become VAB by Z delta. Z delta is the impedance of the load per phase. IBC will be VBC by Z delta, ICA will be VCA by Z delta. So, now here you can say that these currents have the same magnitude, but these will be out of phase with each other by 120 degree, because these voltages are out of phase with each other by 120 degree. Now, we have another way to obtain these phase currents. How? We will simply apply Kirchhoff voltage law to the balanced Y delta connection. So, let us see this particular figure, and to apply KVL we will consider the loop, that is A, capital B, small b and A. That means that we start with A, then we come to capital A, then go to capital B, small b and N, and then come to. So, this will be the loop in which we will apply the KVL. So, we start with neutral point of the source. So, we can write minus AN, minus VAN, then we have the load impedance. So, we can write IAB into Z delta, and then plus VBN equal to 0. So, when you simplify, you will get IAB is nothing but VAN minus VBN by Z delta. What is VAN minus VBN? This is nothing but the line voltage coming across the source. So, we can write VAB by Z delta. Now, since VAB is equal to the phase or line voltage across the load, we can write V small a b equal to V capital A B by Z delta. So, in this way also you can find the value which is same. Now, to find out the line current, what we have to do? We have to take the phase current which we derived and apply KCL at the nodes A, B and C. So, now if you apply KCL at node A, what will happen? IA plus ICA will be equal to IAB. So, you can simply write IA plus ICA is equal to IAB, or you can write IA equal to IAB minus ICA. Now, what is ICA? ICA is nothing but IAB angle minus 240 degree. So, what we will write? We will write IA is equal to IAB minus ICA, that is, you can take the IAB out, and in the bracket you will get 1 for IAB minus 1 angle minus 240 degree for the ICA. So, if you change the phasor notation into rectangular form, you will get 1 plus 0.5 minus j 0.866. So, if you take root 3 out from this expression, you will get IAB into root 3, and in the bracket what you will get? You will get root 3 by 2 minus j 1 by 2. So, what is this? This is nothing but angle minus 30 degree. So, you get IA, that is the line current, equal to IAB into root 3 angle minus 30 degree. Now, similarly for IB, you can calculate the value, that will become IBC root 3 angle minus 30 degree. IC will become ICA root 3 angle minus 30 degree. So, from the line currents you can simply say that the magnitude of the line current is root 3 times the magnitude of the phase current in delta connected load. So, for the delta connection, the line current will be equal to root 3 times of the phase current. Now, what you can write? You can write IL is nothing but the magnitude of IA or magnitude of IB or magnitude of IC, because we assume that the load is balanced. So, this will be equal to your root 3 times of IP. And what is IP? IP will be the phase current, that is the magnitude of IAB equal to magnitude of IBC and equal to magnitude of ICA. The important thing which we have to keep in mind is that the line current in case of delta connected load will lag the corresponding phase current by 30 degree. So, this you can see from the current expressions that the line current is lagging the phase current by 30 degree. So, if you represent line current as well as phase current on the phasor diagram, if you take IAB as a reference, IA, that is the line current for IAB and ICA, will be IA, and which will be 30 degree lagging from IAB. Similarly, IB will be lagging by 30 degree from IBC, and IC will be lagging by 30 degree from ICA. So, this will give you an idea that how the current in case of delta connected will be having a relationship with respect to the phase currents. Now, important thing you need to remember that the phase current is having value smaller than IA, that is why it is represented in the phasor diagram IA larger than IAB. So, IA will be root 3 times of your IAB. So, this will be larger than this, and it will be lagging by 30 degree from the phase current. Now, there is an alternate way also to analyze the circuit to transform star delta connected load to equivalent star star connection. So, in that case what you have to do? You have to convert delta connected load into equivalent star connected load, which we can do with the help of a star delta transformation. So, in that case you can say ZY is nothing but Z delta by 3, and when you put, you can analyze the system as we did in case of star star connection. Now, the 3 phase system here can be replaced by single phase equivalent circuit, which we discuss in case of star star case. So, this will allow us to only find the line current. Then we have to use our recent discussion that phase currents are obtained by the line current is root 3 times of phase current. So, phase current you can obtain with the help of this relationship, and we utilize the fact that each of the phase current leads the corresponding line current by 30 degree. So, this will help you to analyze the star delta circuit while you convert star delta into star star combination. Now, let us take one example. Suppose there is a ABC phase sequence star connected source with the phase voltage VAN equal to 100 angle 10 degree, and it is connected to a delta connected balanced load with impedance 8 plus j 4 ohm per phase. We need to calculate the phase and line currents. So, the load impedance you can convert it into phasor form. So, it will become 8.944 angle 26.57 degree ohm. Now, the phase voltage VAN you can simply write, because it is given in the question, that is 100 angle 10 degree. Now, what will be the line voltage? Line voltage VAB is nothing but VAN into root 3 angle 30 degree. So, we get 100 into root 3 angle 10 degree plus 30 degree, because 10 degree is the phase voltage angle and 30 degree is added because of the line voltage. line voltage in case of star connected leads phase voltage by 30 degree. So, when you simplify you get the line voltage, that is 173.2 angle 40 degree. Now, in case of star delta combination, you know that the line voltage of the source side will be equal to phase voltage at the delta side. So, you can easily find out the value of phase current. Phase current will be VAB divided by the per phase load impedance. So, you put the value of VAB and Z delta and simplify, you get IAB is nothing but 19.36 angle 13.43 degree ampere. Similarly, for IBC also you can calculate with the help of IAB which you got, because the circuit is balanced. So, you can just add minus 120 degree in IAB, you get the value of IBC. Similarly, ICA you will get as 19.36 angle 133.43 degree ampere. Now, what will be the line currents in case of the delta connected load? Line current, that is IA, will be equal to IAB into root 3 angle minus 30 degree. So, IAB we have calculated. So, we will put the value of IAB, then multiply by root 3 and the angle will be subtracted by 30 degree, and when we simplify we get IA is nothing but 33.53 angle minus 16.57 degree ampere. Similarly, IB you can calculate and IC also you can calculate. So, in this way you can analyze the circuit if it is star delta, if it is in the star delta combination. Now, let us talk about the balanced delta delta connection. So, in this case if you see this particular circuit, this circuit is delta delta connected. Here the source is delta connected as well as the load is delta connected. So, the source voltage, that is VAB, and VBC and VCA will be applying across the load impedances also. So, if the line current is IA, IB, IC, in the load we consider phase current as IAB, IBC and ICA. Now, since both are balanced delta delta connections, we will not be able to put neutral from source to load, because we cannot identify neutral in case of delta delta connection. Now, if we assume positive sequence, that is the sequence is ABC, the phase voltage for a delta connected source will be VAB will be nothing but the phase RMS value angle 0 degree, VBC will become VP angle minus 120 degree, VCA will be VP angle plus 120 degree, or you can say VP angle minus 240 degree, both are same. Now, since the line voltages are same as the phase voltages in case of delta connection, delta connected source as well as load, if we assume there is no line impedance, means there is no impedance for the transmission line is lossless, then the phase voltage of the delta connected source will be equal to the voltage across the impedance. So, in that case V small a b will be equal to V capital A B, that is source phase or line voltage equal to load phase or line voltage. V small b c will be equal to V capital B C, V C A will small c a will be equal to V capital C A. Now, from the voltages what we can do? We can obtain the phase currents. So, in this case the phase current, that is IAB, will be equal to VAB divided by Z delta, or you can also write in terms of source voltage, that is V small a b divided by Z delta. Similarly, IBC will be V capital B C divided by Z delta, or V small b c divided by Z delta. So, this is your load voltage which is equal to the source voltage. ICA will be I capital C A V capital C A divided by Z delta equal to V small c a divided by Z delta. So, you can see from the current equations that the currents have the same magnitude, but these will again be out of phase with each other by 120 degree, because these voltages are out of phase with each other by 120 degree. So, now you have the phase current information. Next task is you need to find out the line current. So, how you can find out the line current? You can simply apply KCL at the nodes, either A or B or C, you can apply the KCL. So, here if you apply KCL, you will get IA plus ICA equal to IAB, or you can write IA is equal to IAB minus ICA. Now, ICA is IAB angle minus 240 degree. So, what you can write, IA is equal to IAB minus ICA, IAB you can take out. So, this will become 1 minus 1 angle minus 240 degree. So, if you put the value of 1 angle minus 240 degree in rectangular form, the expression will become IAB, within bracket you will get 1 for IAB plus 0.5 minus j 0.866. So, from this if you take root 3 out, so what you will get, this basically will be 3 by 2 minus j root 3 by 2. So, this is what the actual expression is. So, if you take root 3 out, so this will become IAB into root 3, then this will become root 3 by 2 minus j 1 by 2. So, what is this? This is again the angle corresponding to minus 30 degree. So, you get IA is nothing but IAB root 3 angle minus 30 degree. So, this is the same which we calculated in case of star delta arrangement, where IA was same as IAB root 3 angle minus 30 degree. So, what will be IB? IB will be IBC root 3 minus 30 degree, IC will be ICA root 3 minus 30 degree. So, you can conclude that in this case also the magnitude of line current will be root 3 times of the magnitude of phase current. So, you can write IL is equal to root 3 times of IP. Now, here also you can use the alternate way of analyzing the circuit. You can transform the delta delta connected circuit to an equivalent star star connected circuit. So, what you have to do in that case? You have to use star delta transformation on both sides, convert them into star star combination. In that case, your load will be ZY equal to Z delta by 3. So, this is what we can get from the star delta transformation. So, using that, when you convert delta delta connected circuit into star star connected circuit, you can simply analyze as we discussed in case of star star connected circuit in the last lecture. Now, let us take the example related to our balanced delta delta connection. So, in this case the balanced delta connected load having an impedance of 20 minus j 15 ohm is connected to a delta connected positive sequence generator having VAB equal to 330 angle 0 degree volt. What we have to find out? We have to find out the phase current of the load and the line currents of the circuit. Now, we have got the load impedance from the question, that is 20 minus j 15 ohm. So, we can simply convert it into phasor. So, that will become 25 angle minus 36.87 degree. VAB is given 330 angle 0 degree. So, in case of delta delta connected circuit, VAB will be equal to VAB, which is voltage across the load. So, IAB we can calculate as VAB divided by Z delta. Now, VAB we can put the value of 330 angle 0 degree, Z delta will be 25 angle minus 36.87. So, when you simplify, you will get IAB is nothing but 13.2 angle 36.87 degree ampere. Similarly, IBC you will get 13.2 angle 83.13 minus 83.13 degree ampere. ICA you will get 13.2 angle 156.87 degree ampere. Now, from the phase currents you can find out the value of the line current. Line current is simply IAB into root 3 angle minus 30 degree. So, IAB you have just calculated. So, you put the value of the phase current and multiply by root 3 and subtract the angle by 30 degree. So, when you simplify you get the line current value as 22.86 angle 6.87 degree. Similarly, IB you will get IA angle minus 120 degree, because the line current IB is lagging phase line current IA by 120 degree. So, you will just simply put the value of current IA and then subtract 120 degree angle from the angle of IA. So, if you do it you will get the value of IB as 22.86 angle minus 113.13 degree ampere. Similarly, in case of IC it will be IA angle 120 degree, because IC is lagging current IA by 240 degree, or if you translate it will become IA angle plus 120 degree. So, you will just simply add 120 degree angle in the angle of IA, you will get current IC as 22.86 angle 126.87 degree. So, with this we can close our today's session. In this session we discussed about the Wye-Delta, that is popularly known as star delta, and then delta delta connected circuits. So, in the next lecture we will start our discussion with the delta Y connected circuit or delta star connected circuit. Thank you.